Hello there. Purpose of today's video lesson is to talk about what integration actually does for us. This is the basis for what's called the fundamental theorem of calculus, and it just goes over some of the theoretical understanding of where the integral sign comes from, what's the dx all about, and why do we even integrate. To starters, the derivative always told us about the average or the instantaneous velocity or instantaneous rate of change. So we knew that when we studied a function and we took its derivative, we would be learning something about the slope of the tangent line. But what is the antiderivative or the integral for anyway? So to get into that, I wanted to show you where the basis or the origins of integration came from. So here I have an arbitrary function. It doesn't really matter. It's just a cubic. And I'm interested in the area under this particular curve from when x goes to 2, x goes from 2 to 4. Now, as you can see, I have the curve, and I have this green rectangle, and the rectangle is producing an approximation of the area of that curve. And what I'm going to do is, I'm going to increase the intervals to 2. There we go. And let's just do it the old-fashioned way. Give me a second. Change that to 2. And now you can see what I've done is I now have a better estimate of the area under this curve because I went and took 2 rectangles instead of 1. So the first rectangle goes from 2 up to the curve and then over to 3. And then we go from 3 up to the curve and over to 4. And that produces 2 rectangles and a slightly better estimate of the area under the curve. Clearly, you should be able to notice that if I increase the number of intervals, I get a better and better and better approximation of the area under the curve. I keep doing that over and over and over again, and eventually you can see I have 100 intervals, and you can't even see the rectangles because even with 100 intervals, it looks curvy. Now, if we were to zoom in on this spot, we can now see the rectangles. Clearly, they look like steps, but if we zoom out, it's just curve. So clearly, the more intervals we have, the more we break that big rectangle into little tiny rectangles, the better approximation we have for the area under this curve. So this gives us the ability to find areas for curvy shapes. This is what calculus is good for. So to get back to the boring stuff, or the slide here, this is a representation of what I showed you on the Desmos graph. It's showing an arbitrary curve again, and I'm interested in the area underneath that curve. In the first image, I have 4 rectangles to approximate the area, and they each have an area that's represented by a change in x. So I took the distance that I wanted to find area for and divided it into 4 equal parts, and that's where delta x comes from. It's all the same width. For the heights, though, I'm going to take my first x value, calling that a1, and find the value of the function there, and that produces the height of this rectangle. Put a2 into the function to produce the height of the rectangle, and a3, a4. And that gives me 4 rectangles of uniform width, and they each have a different height, and if I add all those areas together, I get an approximation. It's going to be an underestimate, but an approximation of the area under the curve. Now let's look at the notation. The red rectangle is f of a1, so you can see that's the y value representing the height of the rectangle, so it's f of x1 times delta x. Delta x is the width of the rectangle. Then I have delta x again for a different rectangle times f of x2 plus delta x times f of x3 and delta x times f of x4. So this produces the area of all 4 rectangles. Now mathematicians, instead of having to write out all 4 of these, developed a notation called summation. It starts with this sigma, which is the Greek letter for uppercase S. I don't know how they got an S out of that, but that's the letter sigma. And it's saying basically we have starting with 1 partition going all the way up to the 4th partition, we're going to calculate the delta x for the width of the rectangles and f of each of those x's, x1, x2, x3, x4. So this is a shorthand for an approximation of 4 partitions under the curve. Now here you can see I added 7 partitions. It's the same general width, but I divided that width by 7 equal parts. So now I have a new delta x. My new delta x is a little bit smaller, and my approximation is a little bit purer. I'm seeming to be having some trouble with lag in my pointer right now. This is going to really mess up my video. But hopefully some point I'll try to point down here. Maybe I can highlight this. Goodness gracious. Alright. Well, let's just cut to the chase. I'm going to just point out when you look at this diagram that there's more rectangles and they're smaller, and I get a better approximation. So if, as you can see in this slide, and I can't point to it, unfortunately my arrow just shows up in that one spot, and can't highlight this at all. Next to the graph, the top Mathy equation shows what's called a limit, and I'll just cut to the chase. If you allow the number of partitions to go from a few partitions to infinity partitions, then that Greek letter sigma becomes the integral symbol that we saw before, which is also like the letter S. Also notice the delta x, which is the triangle x, now becomes dx. So the act of making infinity partitions changes my mathematics from a sigma of a finite number of rectangles into the long S, or integral of infinite number of rectangles. So all that talk just to tell you that the dx is actually the width of all of my infinity rectangles. F of x is the height of all of your infinity rectangles, and if we go from A to B, those are the boundaries, as you can see on this graph, from A to B. That'll give me the area underneath. So I'm going to have the next video is going to show you the work that you need to actually do, but essentially this is the fundamental theorem of calculus. Essentially, if you want to find the area under a curve, all you have to do is take the antiderivative of that curve and subtract at the endpoints, and that produces the area. I'm sorry I got flustered. I lost my pointer, and it's got a little weird, but anyway, I just watch the second video to know how to do what you need to do, but at least I hope you can gain some appreciation for why the integral notation is what it is. In the next video, again, I'll show you how to actually calculate the integrals and what notations to show and how to check your work. So thanks for watching. Have a good day.